into my, can we go over to full screen right monitor? That's going to be zoomed in. So let's, I guess I could kind of put that on the, we're not going to worry about it. We're going to just keep this full screen here while I go into my files and find that recording we just did, and we're going to use it to upload that to YouTube as a little tutorial. So I'm gonna guess it's probably the 2020 1203 whatever, or maybe not, because that is kind of 158 megabytes really for just that small recording. I guess. So let's take a look at that and see what we have. Okay, so that looks good. So that is what we want. So I'm going to rename this as, I'm going to rename this as, let's see, SDF18 setup. Yeah, might as well call it SDF 18 setup .flv. And I don't know where I want to put this, I guess. I'm going to put it in code told fast / shader toy. And let's go to YouTube. And let's log out. Let's log out and log back in as code told fast. So let's see. Sign out. Please don't log me into something else, because I don't know, I've lost a whole bunch of accounts because when Google decided to like merge Blogspot with whatever else the hell they merged, I lost some old YouTube channels. So let's sign in, and let's sign in as code told fast. Okay, and we're not going to add any recovery stuff, because also you would have saw that, and also I'm sick of getting locked out of my stuff. So 90 videos. No, this guy. Okay. And so here we're going to okay, so here we'll upload that. So we're going to I'm gonna go over on, let's move this over here because I have no clue. I have no clue what's going to open when I do this. So let's keep that off screen just to be safe. Alright, select files, stream folder. Okay, so let's see. And then what we can do is we can take all of these URLs here and we can kind of... Oh, it's not going to let us do that? Yeah, we're not gonna do that. We're just gonna source. We're just gonna keep source code. And then we're also going to keep the source code and live demo. And paste Unicode. Source code, live demo, and do we want to keep Twitch in there? I think that if we have more than 3 things in the description, it truncates the description. So we could try to put that in there, but I don't know if that'll be good. I don't want the description to be truncated, so I only want the important stuff to where people know where to go if they want like more information, right? So in the playlist, we're gonna do a new playlist and shader toy. We'll make that the list can be public, and we'll create it. We'll put it in shader toy. And it's just the code setup, right? And so we're going to keep all of this to just code setup for shader toy, because this is code told fast, so we're just trying to be as quick as possible. So there's not really going to be anything unique, right? Like if you've seen the code before, there probably won't be anything unique, but it's just good to have a YouTube video for this documentation. So Code Told Fast is supposed to be a channel that's very concise, where we don't go ranting forever, so let's keep it to that. Code setup. Okay. No, it's not made for kids. More options. We'll, technically, I'm science and technology. Allow all comments. Sort by newest. Let's go back, because that was a bad preview. We should have a selection between, like, 3 different preview images, right? Like, in the details. Oh, wow, they're all like Bart Simpson. Okay, yeah. So that is what we want. Save or publish. We're gonna make this public. And publish. Okay. I'm just reviewing this, making sure it's right. Okay, that's good for me. So let's edit this video really quick. Let's edit the description, because I see that it looks like I could have 3 pieces of information without them being collapsed. So let's refine that Twitch URL and close. Okay, so we're just gonna say live stream of me working on this code. So I guess we already have source code, so we don't need to explain live coding stream. Okay, we'll paste some Unicode characters so that we can get back our monospacing. Source code, live demo, live coding stream. Okay. That's good for me. Let's keep that as a template. File, new text document. I'm gonna store that in a description. I'm gonna store that in a description.txt. Or actually rename SDF18 setup.txt. I'm just going to put that there so that I have a way to cut and paste this for next time. And that is weird. That's not the same. I guess maybe my font, so settings, preferences, or not preferences, settings, style configurator. So we're doing Andale Mono. What about Anonymous Pro? What about Monaco? Monaco, where are you, Monaco? Huh, really? How about Noto Mono? Huh. How about Osaka? Okay, so I guess I didn't know that before, but I guess none of my programming fonts. I used Osaka when I was programming stuff in Japanese because I was being batshit crazy. But yeah, I guess the Unicode characters are not completely monospaced when oh, I see. Looks like depending on the font you're using, the underscores can be double wide. Oh well, whatever. It's there. Okay, so we've edited that. Let's save those changes. And let's make sure that that kind of looks correct when we are looking at the video. And if that looks correct, then we're kind of done here. Okay, so that's good. So let's take that and let's take the URL for that YouTube video, and let's put that into our list of things, right? So we got youtube.com/watch, and that's a problem. Let's find YouTube short URL. So I think it's YouTube short URL. There should be a short URL for this kind of stuff. So let's except they're still pretty long. u2.be u2.be slash, I think I can do the video like that, yeah? Let's try that. Good enough. Good. That's good enough for me. So, u2.be, right? Yeah, that's it's still pretty long, but you know, it's short enough to fit within my column limits. So I say that is good. So then we can take the we can actually take the we can just take the full URL for tinyurl.com. tinyurl.com. And we'll do we'll take it, and then we'll do SDF-018-setup. Set up. Okay. And now we have that URL, and let's make sure that when we go to it, tinyurl url.com/sdf-018-setup. All right, cool. Okay, so let's take now that we have all that in place, let's do one last pass and update all of our paste bins and the shader toy project, and then we're done here, and we can continue on to the next step of the tile map stuff. So let's go to www.tinyurl.com/sdf-018. Okay, and let's do edit. Go Control A, Control V, save changes. www.tinyurl.com/sdf-018.buffer. We'll edit this. We go Control A, Control V, save changes. Then we'll go to image, so tinyurl.com/sdf-018-image. And we'll hit edit. Control A, Control V, paste the image. And we'll save those changes. Then we'll go to www.tinyurl.com/sdf-018-demo, right? So we'll go to the shader toy, and we're gonna just make sure that that is all in sync as well. So we'll take the buffer, and we'll go to buffer A, we'll take all that code, we'll paste it back down in there. Then we'll take the image code, copy it all, paste it in there, make sure everything works, and then we will then we'll save it, right? Okay, so yeah, we got that in place, and now the next step is to do kind of like tile map setting stuff for the next so the next thing we're going to do is we're going to make a rudimentary two-dimensional tile map, and in the shader will do like a texel fetch on that very specific pixel to know that it needs to do a 2D rendering of the tile map, and we'll use the 2D render view to make absolutely sure that, you know, we're setting the values we think we're setting. And it's going to be really rudimentary, so we're just going to keep it like we're just going to subdivide the screen into 64 by 60, actually 63 by 63. Yeah, we want to do 63 by 63. So we'll just subdivide the screen into 63 by 63 cells, and we'll just kind of click on those, and it'll be distorted, right? We're not going to worry about keeping the tiles square, because it's just going to be for a really hackish like user interface. We're not going to yeah, it's just going to be a hackish user interface. It's not going to be meant to be like a finished thing, because the 3D view is really what we care about. The 2D view is just kind of like a little control panel to help us debug the data, right? So let's oh, also, is this still is this still unlisted? Yes, this is still unlisted, so let's make this public now that we've kind of like set everything up. And hit save. Okay. So for the next stuff, all we're going to do is we're going to take all of these files and we're just going to copy them over, right? So we're going to take this and we're going to... now, if I do a save as, is that going to save it as something, and then that's going to be the new file name, or do I have to, like, reopen it as well? So SDF19. Oh, okay, cool. File, save as, and we're going to name this SDF19. And then we're going to go over here, and we're going to do save as, and we're also going to do SDF image, and we're going to do 19. Okay, and if we open the Explorer in Notepad++ and just look to see that we have everything here, and I see, yeah, we got 19. Okay, cool. So now that we've kind of copied everything over, we can just change those to 19. We can change this to 19, and you know, hopefully, the worst thing I can think of is, you know, eventually if I actually get a lot of viewers, that this will become a problem where people are going to identify this pattern and they could, like, literally hijack this. I guess one way that I could fix that is I could do a session of kind of like pre-reserving these, right? Like reserving these numbers like 100 units ahead of time or something, right? Just so that when the time comes, it's there. And but right now I don't have to worry about it. In fact, until I get actually screwed over on this, which I don't think it'll happen until I actually get like a whole bunch of viewers and then somebody just wants to throw a monkey wrench in my stuff. Until that happens, I'm just going to keep on not worrying about it, right? I'm going to just go about my business. SDF19 does not exist yet, so somebody, if they were watching this stream, could just claim that and screw with my day. But, you know, until there's a large amount of people watching, I don't really think I have to worry about that, because it's not like... most people, I don't think are, what do you call it, chaotic evil. I think that would qualify as chaotic evil. So, let's take all those, right? So we got them all blanked out. And then over here, 19 and 19, right? So we don't even have to worry about the... we don't even have to worry about changing the URLs here, because we already have them set over here, so we're fine there. About voxel engine work, rude, voxel engine 63 by 63 by 63 by 63 vox holes. Voxel map. Long-term goal. Two. Okay, so now I'm just kind of, since we have this agenda and whatnot, and there's none of these descriptions in these other things, we can kind of just work on that here. So okay, so this is our agenda. This is our agenda right now. This file will do. This code does. Okay, so we have what this code does: sets tiles on a 3D voxel map using a rudimentary 2D tile map view. About voxel engine work, we have some long-term goals: 63 by 63 by 63 voxel map, not 64. So it's very intentional that I'm doing 63 by 63 by 63. And then we have long-term goal number 2, fractal 3D auto tiling. Okay. So store. Okay, so that's good. So we have a nice little description here. And then we have like our little documentation. And let's not worry about all of these URLs and stuff until the code is well, if we do that, you know what, unless somebody's going to ask me about the code, right, if somebody asks me for the source, we can do that, but let's not worry about pasting the source until like we're completely finished, right? Because otherwise we'll waste a lot of time cutting and pasting that source all of the time. So let's not do that. And let's go to the new tab and let's paste all this stuff in here and get it all set up, right? So we're gonna take the buffer code. Oh, actually, we're gonna take the image code first. So bids, image, and then demo. So whatever. Anyways, I'm just getting distracted by the ordering of my tabs. Okay, so let's take that, and we'll paste it in there. And then we'll take the buffer code, and we'll make a buffer A, and we'll paste that there. Then we will set up the buffer. So I'm pretty sure we do need the buffer in both slots. So let's do buffer A. And let's go over here to the image tab now. And in the image tab, we'll also add a buffer A. Okay, now with that set, we can actually... yeah, we can actually see it. Okay, cool. So I guess, like, you could think of the buffer A and the image being, we need to read from the buffer A, and so we're going to put it in channel 0. That's where we're going to wire it up to. And then This buffer A tab is the code that controls buffer A, and then buffer A is in channel 0. I'm not sure what the difference between the buffer A tab is and this buffer A down here. Like, because, yeah, I'm not sure exactly how that works in the exact relationship. But let's just keep it simple so we don't have to worry about that, right? I don't know exactly how the wiring up works. Like, it seems like when I put a buffer B in channel 0, things don't wire up. So I don't know if buffer A is like a unique allocation, so that if I put a buffer A in channel 1, then it would be the same allocated memory, but channel 0 and channel 1 would just both point to that same buffer. Judging by the fact that in these two different tabs, we have the buffer A, and they're both set in channel 0, I'm going to kind of assume that buffer A is like one reference, right? And the channel is a handle or a pointer to. Not really a pointer, let's just call it a handle. The channel is a handle, and that handle is unique to the setup for these individual tabs. That's the way I understand the setup here. So anyways, we got that set up, and now what we want to do is we just want to call it like tinyurl.com slash SDF-019, right? And then we're going to keep that private. Actually, we're not going to keep it private. We're going to keep it unlisted in case somebody wants to go to it. And we're going to say basic rudimentary 2D tile map view of cross-section of voxel map 63 by 63 by 63 data. And tile map voxel map tile setting. Okay, so we got like a little description, and that looks good to me. Let's it's unlisted, so we can hit submit. And I noticed that even if it's unlisted, it can still be, people can still find it, I've noticed. So let's take the let's go to www.pastebin.com and at least put the SDF let's put the SDF 18 in there. So SDF 18 and GL, and this isn't SDF 18, this is SDF 19, is it not? Yeah, it's SDF 19, so we actually need SDF 19 like that. Create new paste. 19, 19, and 19. So save, and save. And now that we have that URL, we can actually put that we can put that in Pastebin. So Pastebin, this is self, and it's also the documentation. Okay, yeah. Okay, that looks good to me. Okay, so now let's get back to it. So we're over here, and we want to somehow render this as tiles rather than just individual pixels, right? So let's move this back up here. And I noticed that weird things happen when we kind of like when the buffer gets resized. We're not going to worry about that. That's why we're going to stick to 128. Sorry, not a 128 by 128. I keep on saying 128 by 128, but we need 256 by 256. And that also means that I screwed this up, didn't I? This should not be 127, 127. We need to do 255, 255. Yes, we do. So now that I realize that, let's do 255 and 255 in our documentation. And then let's actually fix that problem, right? So in the code, we did 127, 127. That should actually be 255 and 255. And 255 and 255. We could also make a define for that, right? So that is these are like macros that are used everywhere, but this other configuration, so in our configuration, we will set the what do you call it? I don't know. We'll call it we'll do like define state pixel x. It's at 255, and define state pixel y, and we'll do 255. I'm going to do SPX and SPY. The reason for that is I'm going to be as terse as possible, and we'll just keep explanations where the variables are defined. State pixel x, because the problem is if we're not terse enough, we end up getting really wonky formatting, or we end up battling that formatting a lot, and we end up adding extra defines and extra bloat to the code just so that we don't go over this column limit. So in order to like avoid that problem, we need to keep the variables as short as possible, because we can always remove the comments and still have functional code, but we can't do the same for the variables, right? If we can't just remove variables to truncate the line of code, but we can do that for the comments. So let's keep the variables as terse as possible, and then we'll keep nice comments when needed, right? So state pixel x and state pixel y, and then we can do SPX and SPY here, and then SPX and SPY here as well. SPY, right? SPX and SPY, and that will just make it a little bit easier for us to see the difference, because right now we can tell the difference between this 255 and the 255s that are here as well, right? So with that, I don't think we have to do any state pixel stuff over here. There's none of that code there, so that's fine. Let's update the code. Make sure that, oh boy, I have two screens open. No, that's great. This one needs to be closed. I'll leave that there. So in our buffer, I'm going to paste the new code, and I don't really expect anything to have happened. It's just, it's looking at a different pixel, but that pixel still has a non-zero value, so it's fine. Okay, good. So now that we have that, let's figure out how we're going to render tiles. So in SDF019, we need some type of get tile function, right? Because we're not doing a direct mapping of pixel values to tile values because of how we want to optimize use of the space. Partially, we're just doing this because of the limitations of Shader Toy. I would really like a 512 by 512 chunk of memory that I could just use for this voxel map. But since we can't guarantee ourselves that, we're going to use a 256 by 256 chunk, but we'll only use the 1 byte of each pixel depending on what location we're at. So we got to figure out how we're going to do the mapping for that and what intuitively makes the most sense. We could geometrically subdivide the space, right? Because we could do like the 64. We could use like a little 64 by 64 chunks of memory. And if we did that, what's the most useful abstraction? I think the sooner we get the data into like a useful abstraction where like we could just transform it from, right, because all the data is all linear, right? It's just all data is just a one-dimensional array, and then we abstract it into 3 dimensions. But if we just have some type of direct linear mapping between the data and the tile value, it might not transform in what I would call like coincidentally pleasant ways, to where like if we just use a linear transformation, then if we took a snapshot of the data and we just opened it in MS Paint, like we took a snapshot of the texture and we opened it in MS Paint, and we can't make sense of it just because it's just like this linear array of data, and right, like I think that there is an advantage to geometrically organizing this data so that if we want to diagnose a problem, we can look at the actual texture, and we can, from just looking at the actual texture, we can see if anything is strange from looking at it, right? And that requires us to organize the texture pixels in some type of geometric way, right? So I think we want some more thoughtful geometric way of packing our data in there, so that we can diagnose the problem, right? So let's think about how that's going to happen, right? So we know we already have like a 256 by 256. So what I'm thinking is we're going to have these blocks. It makes sense to, I'm gonna actually, before I start trying to do ASCII, because ASCII is is very ASCII is kind of hard to uh, it takes a while to draw out, so until we actually know exactly what the layout is, we should just do pen and paper. I suck at math, so even though that was pretty simple calculation, let's absolutely make sure that we're correct with that assumption. If we take 4, we multiply it by 4 by 4, and do we get 64? Yes, we do get 64. Awesome. So that's how we're going to segment the data. Even though our voxel map is going to be 63 by 63 by 63, programmer numbers are, friendly with powers of 2. So we'll just, in our rendering, we're just going to discard the 64th tiles. We're just going to discard that data. And I have reasons for why I want to do it that way. Also, that kind of gives us a convenience where we can use the borders of the texture memory for other useful state values, right? So let's add that little diagram into our documentation. So now that we've actually drawn out our visualization of what needs to be done, we have the tools we need to kind of like effectively start sketching this out, right? So we have the R, and we have the G, and then we have the B and the A. And we want to keep the consistent ordering. So R, G, B, and A will be more like so R will be the first cross sections 0 to 15. Is that 0? Yeah. So when we're thinking about this, we should try to keep some type of order that makes sense. So R, G, B, and A. With R, G, B, and A, we have, this is going to be 16 to 31. And this one will be 32 to, 47, I think? And this will be 48 to 64. Does that make sense? Let's double check the 48. So if we do 47 minus 32 plus 1, do we get, what do we get? We get 16. Okay, cool. So 16 and 16, 32, 32 and 32, 64. So that looks good. That diagram makes sense. Let's go to the other parts. So let's diagram this as 512. 512. And make a note that 512 times 512 equals 64 times 64 times 64. So that's an important note, to note that our voxel data set that's 64 by 64 by 64, 64 by 64 by 64, that is equal to 512 by 512. We want to make sure that we have enough data, right? And so that maps very nicely. And when we're looking at G, so let's say we take G and we kind of like blow up G. So let's take G and kind of blow it up. So G, and G is 256 by 256. 256. And we're just going to assume it's square. We're not going to worry too much about that. And we'll take G over here one more time. And we'll note that can we divide this into 4 cells? Looks like we have just enough room. I don't know how we're gonna do the... One, two, three, and this is 4. By 64. Okay, so, this is just a little diagram, right? So we conceptually think of it as the R channel, the green channel, the blue channel, the alpha channel. And if we zoom into the green, it's 256 by 256. It's half of that. And if we take 256, we can slice it into a 4 by 4, right? That gives us 16. And when we look at, or sorry, not a 4 by 4 doesn't give us. So yeah, it gives us these 16 cells. Yeah, so this is a 64 by 64 cross-section. Cross. Let's just abbreviate it so that we can... So let's just call it CrowSec. Like that. The reason why I want to do that is just so when we double-click the this token, we can see where else it's referenced in the diagram. Right, and so when we're looking at that, that means that we want to zoom into that really quick. So this might be very time consuming, but if we get this correct, right, and this is something that we're actually going to commit to, and it's something if we come up with a nice solid foundation for the kind of stuff we're working on, we can hopefully reuse some of these types of diagrams. But I think it's very important to get your thoughts well organized, right? And so even though this is time consuming, you're kind of collecting your thoughts and making sure that you got a grasp of yourself. I don't know how else to say it, but so we can zoom into this, and that way we can kind of look at what each of these cells are, and not sure how we are going to do this. Hold on. So this is kind of like, it's not the best way, but that'll do. That pipes into there like that. And we could also funnel this diagram into here. Well, technically this is still G, right? We're looking at G. So technically that would not be this. So let's actually go like that. And let's see if we can kind of like make a little tube that goes to G. Let's try to keep it the thickness of whatever this is. Okay, there we go. So I got this little pipe dream kind of diagram. But we kind of know what that's all about, right? Tile data layout. Okay, we can call it tile data layout. Okay, so now we got these nice, beautiful diagrams and not any code, but we have a pretty damn clear way of how we're going to do this, and we're not going to dig ourselves into any holes where we're doing the math and then we realize it's not even possible, right? We know exactly what we're doing here, and we can use that in our code, right? And so what I'm thinking is maybe we could just call it, I don't know, I'm just experimenting here. I don't know if this is the way to do it or not. I'm thinking what we could do is we could, when we're creating these sections, for the different code sections, we could actually and what were we doing in 17 here? I just want to check out my functions here in 17. Oh, I see. So in this code, we kind of like decided like segment things based on what degree removed the functions were. I don't think that was helpful at all, and it added a lot of extra wasted space, I think, like, because it is important to order your functions correctly, but I think this level of categorization I used, where I had these degrees removed, I think that wasn't very useful. I think it just wasted a lot of space, and it wasted a lot of column space, and ended up with all these functions indented one deeper than they needed to be. So we're not going to do that this time. So I just wanted to see how I was indenting earlier. So yeah, I think I want the indentation for functions just to be all the way here, so we're not wasting any space. And data is a little bit different, but functions do not indent the outer scope, right? So let's see, tile data layout. U32. Do we just want to call it get tile? Okay. So the voxel is the tile. Do you want to call it get vox, or do you want to call it we could call it vox for voxel. We could keep the tile map analogy. We could say get tile, or we could call it a vob for voxel byte, right? Voxel byte, or tob for tile byte. Let's see, in our old code, let's look at our old code, and let's look for vob, and I think we didn't use that anywhere, but let's make sure we didn't use it anywhere. Vob and tob. So voxel byte versus tile byte. Would actually be tib for tile byte. Get tib. Well, I know I'm thinking of voxels as three-dimensional tiles. Even though I do want to keep the idea that we are using that voxels are just three-dimensional tiles. I think that that my idea of enforcing a tile map analogy when I might want to use 3D voxel terminology, that might be slightly misguided, because there might actually be two-dimensional data sets and three-dimensional data sets that we're going to use for rendering, right? And so we might want that differentiation. So so what I'm going to do is in our documentation, let's see what we have. We have like a key. We have a key, right? Yeah. So the key is for the okay, so for this, let's vars. So let's say vars funcs get tile byte, tile value 0 to 55, and then get vox, or not get vox, but get vob, get voxel byte, and that one's going to be tile value 0 to 255. So what we're going to try to do in our code is we're going to try to not have so much comments in our code and just have some good documentation and very clear names that have very strict definitions, right? So over here, we're going to say that get vob, and we're going to do U32 voxel X, U32 voxel Y, and voxel Y, and U32 voxel Z, right? And do we need in our data, we definitely did something where we needed to use the index value, and the index value should think So the index value should think that we have a 512 by 512 chunk of memory, even though we don't. And the reason why we want a index value is because we want an index value because I know that our pattern for creating like a stack of where we are within our voxel map, we just want like one integer value that can correctly identify where we are in that space. So we're going to take, instead of saying get vob, we're going to say vob voxel byte xyz. vob xyz, get vob using xyz, vob dex, get vob using dex, right? So have vob and vob, right? Okay. So now vob xyz, voxel byte xyz, and we're gonna try to be kind of like as terse as possible. So we're going to be a little bit more compact than we have previously been, and we're going to maybe avoid the lining up arguments like we were earlier, and try to condense our space. We're going to try like a slightly different style than we did in the previous code. We're still going to meticulously line stuff up, but we're going to try to maximize our space. So we're going to try to avoid white space, and we're going to try to like not only are we gonna try not to go over this column limit, but we're gonna try to avoid like large swaths of empty space within any real estate, right? So, so U32, okay, get vob xyz. So the first thing is I'm gonna open up my little diagram. So now that I have this documentation in a different tab, that makes it kind of nice, because what I can do is I can actually put this documentation over on a different screen, and so you can't see all of this, but now you kind of know, if you see that me looking at this, that's because I'm referencing documentation while I write this, right? So now I can reference these little diagrams while I'm writing the code, and that's going to help me make sure that I'm actually thinking about it correctly, right? So I have those little diagrams on one screen, and I'm going to use those to help me figure out how to do this. So we need to kind of subdivide our space and know where we are. So and this is XYZ. XYZ to index, right? So the first thing is we have to identify what cross-section we're on, right? So Z is going to tell us what cross-section we're on. And that'll tell us if we're using R, G, B, or A, right? Okay, yep. So is that all Z tells us, though? Is that all just Z tells us R, G, B, or A? Yeah, because if it's 16 to 31, okay. So so U32 CCC for cross-section color. And that equals VZ f32 vz divided by 16, right? If it's exactly... Yeah, because if it's divided by 16 and it's 0 base, so 16.0. And it's int and trunk. So we truncate it, we convert it to integer, right? And then the cross-section color. From the cross-section color, we can now zero it out. So we can go U32. So this should actually be cross-section so let's do cross-section now let's do it like that. So cross-section local equals VZ minus CSC times 16, right? And that will give us the local value of the cross-section, right? So if we are at tile 15, if we're at layer 15, then this gives us a value that is less than 1. And when we truncate it, it ends up as 0, right? And then this times 0, VZ minus 0 means it doesn't get, nothing gets truncated, right? Nothing gets taken off. If we end up at 1, then this is 16, right? And let's say this were 16, right? Because that's the first thing that's going to give us 1. Well, 16 minus 16 gives us a 0, right? So it's the first local coordinate of the second cross-section, right? So cross-section color, cross-section layer. So let's take these for a second, and let's put those into like our little key over here, our key in our documentation. So, and we'll just keep like a running total. So we're gonna forego putting any of the comments in the code, and we're just gonna put them all here, right? So cross section color, cross section local layer index 0, 1, 2, 3. Okay, and now that we have a local cross-section layer, we know what cross-section we're in. Great. So let's see, what else do we have to do to interpret where we are in this data here? And then after this, I'm going to go to bed once we kind of figure this out. Cross-section layer. So then each one of these segments, these are the different, so within, let's say we're in the green section, well now, we could say these are the green floors, right? There's the red floors, the green floors, the blue floors, and the alpha floors, right? We could think of those as different floors, like maybe you have a skyscraper, and the bottom 16 floors are red, the next 16 floors are green, the next 16 floors are blue, and the next floors after that are alpha, right? Maybe they're just clear, right? It's a fancy clear penthouse with a pool and a nice view, and then it's clear because they want to be able to see out the windows, right? So with that, we know that we want to find the cross-section origin, right? Okay, so what we need now is we need U30 cross-section index. So the cross-section index is equal to before we do that, so we're still looking at Z, right? Yeah, we're still looking at Z. So cross-section color, cross-section local, so the cross-section local is that index, isn't it? Yeah, that is the index. So going back over to our notes here, okay, so cross-section index is the same thing as cross-section local. So so this is these are all the different local cross-sections, right? Because these are 64 by 64, and these are within a certain set of floors, right? So we got the cross-section color. This is cross-section color, and any of these values would be the local cross-section value. So what we need now is we need to take that index and we need to convert it into an XY value. So we do index to XY, and then we just take this basic formula, index to XY, no modulus. That's the old stuff, so let's try to find that, where that is, and update that. I'm pretty sure we want ITXY, use ITXY no modulus 2020. Yes, that is what we want. ITXY no modulus 2019. ITXY no modulus old. Okay, so let's okay, so let's look at this ITXY. This still isn't the best version of what we need. So let's look at. Let's just. This is where sometimes memory is just better. So, let's just do the math rather than try to look at our shortcuts, because it's going to take longer to find our shortcuts than it is to rethink about what this math is, right? So we're trying to so U32 CSX or X or Y, I'm not sure which one. X or Y, not sure. Equals CSL. And this is the index. And we're going to divide by 16.0. And this is F32 CS. And you could almost think of this as lines now. And the number of these full things is going to get us the Y, right? Yeah, so CSY divided by 16. And then int and trunk. Okay, and then U32 CSX. And we're going to take the CSL, and then we're just going to minus CSY, right? So, oh, not just CSY, but CSY times how many lines there are. So the CSY is the number of filled lines, and there are 16 on the X for each of those, right? And it might be good to make a note that 16 is the width. So in here, I think and 16 isn't even the... Why the hell did I use 16? Oh, because I had 16 here, but it's actually 64 by 64. Why are these 16, though? Did I have a reason for that? Yeah, because there's 16 cross-sections. I'm gonna try color in that. 16 floors of each color. Do I really want to color it like that? 16 floors of each color. And this is each floor is 64 by 64. Sixteen floors of each color, and each floor is 64 by 64. We're gonna use ats for things that are simpler, right? Things that I don't wanna like write whole sections for. Extracted comments. At analogies. Analogies or analogies? Analogies. Analogies. IES. Okay. Okay, 16 floors each color. That's good. Each floor is 64 by 64. And okay, that's good for me. So CSX, we're gonna take the local of the Z, because this is the cross-section color, right? We're going to take Z, divide by 16, and truncate that. Then we take off the cross-section, right? So now the Z value is this local value, and we can step into this local value is like which local floor number within a certain color we're in, right? And we can use that as an index into the data, and the Y in the index will be the Y will be however many full lines we have, and the width is 64. And then the X will be whatever's left over, so we'll take the index, so we'll take all of them, and we'll minus how many full lines we have, right? And that should give us the answer there. Okay, so now we have CSX and CSY. Um... And CSX and CSY actually, CSX cross section cell 64 by 4 location x axis. So CSY is cross section cell 64 location y axis. Okay, so what I mean cell 64 is that one of these things here is a cell 64. So let's open this up again and say that, you know, this is a cell 64 with index equal 14. And this is, if we want to look at that and think about the math here over here, this is CSL equals 14. CSY should equal to, there's X, there's Y, 1, 0, 1, 2, 3. And CSX equals 0, 1, 2. Okay, so now the question is, well, why do we need that? Why do we even need the X and Y derived from there? Well, it's because we're gonna treat we're treating this as a floor, and so we need the X and Y. Oh yeah, because it's the X and Y of a cross section, right? Oh wait, is that not correct? Oh, that's not correct. Oh, that's why we do 16, right? The 16.4. Okay, so this should actually be 4.0, right? On a (16) 64 by 64 floors on 4 by. Okay, so there's 16 64 by 64 floors on a 4 by 4 grid. Okay, so we're actually... Okay, so we get the local... So first we got to figure out what color the floor we're on. Then we multiply that color, 0 to 3 by 16. And then we subtract, that should be U32, 16. So then we subtract it to get this local floor index. And this local floor index we use as an index into this two-dimensional array of all the floors of a certain color. And this array is going to be 4 by 4, right? So this is, right, this is obviously 4 cells here. Okay, 4 cells. Okay. And since those are 4 cells in our tile map math, we use 4 and 4. And CSX, CSY. And that's still a 256 section. So then all we got to do is we take U32 cross-section origin x equals CSX times 64, right? U32 64. And U32 cross-section y, CSY times U32 64. Cross-section x, cross-section y, cross-section origin, right? Okay. So that's cross-section cross-section origin. One is x, one is y. Pixel of okay. Cross-section x, cross-section y. And all I gotta do is multiply by 64 because in our little diagram down here, in our diagram here, right? Each one of these cells right here is 64 by 64. 64, 64, 128, 256, right? So this entire area is 256, and it's the green section, right? So with that, we have found we found the origin, right? And then the x and the y kind of will go into that further, right? Yeah? COX, cross-section origin x, cross-section origin y. And then so then we'll take U32 px. So now the actual pixel is the cross-section origin x plus the voxel x, right? U32 py equals cross-section origin y plus the voxel y. And U32, there is no actual, there is no actual pixel z, right? It's actually two-dimensional texture, so there's no such thing as pixel z, right? So pixel x, pixel actual, pixel x location on texture. Py is actual pixel y location on texture. Pz, no such fucking thing, 2D texture. Okay. So this is px and pz. These are the actual pixels. And then what we're going to do is we're going to take the with that pixel, so we'll do a texel fetch, and let's check out our reference. So texel fetch and I channel 0, then IVEC2, and we'll do px and py, and the level of detail 0. And this will be U32 color 4D. It's a color 4D value, so we'll keep on using C4D for that. C4D color 4-dimensional float values. Vec4 type. Color 4D. So this is the color 4D. And with color 4D, like we already kind of we'll just try to smash that in there nicely. Okay, so with color 4D, we'll do if the cross section 0 equals U32 0, equals cross-section color, and red byte. Alright, so, byte. Byte equals, U32, C4D, divided by 255 point, color 4D is actually a V4. So C4D.X for the red channel. Divide that by 255 to get it in the, or not divided by, multiplied by, right? Yeah, multiplied. Why do I have... yeah, because this is a 0 to 1 value, so we want to multiply it by 255. Okay, else. And we want to keep on doing the same thing for each one of these other things. So red, green, blue, alpha. And there should not be any else. Else. This is an error. Okay. And 1, 2, and 3, right? And we're gonna do X, Y, Z, W. X, Y, Z, W. So that's kind of verbose. Can we access, can we do array access on vectors? Array access vec4. Can we do array access on a vec4? So I'm not sure if we can, so we're just gonna... This is ugly as hell. So it'd be nicer if, so let's comment this out, just in case this is how we need to do it. And let's say that U32 BYT equals, and we'll do equals U32 color for D, and then within the brackets we'll do the cross-section color, and then times 255.0, right? That's how I want to do it, right? We get the byte value like that in one thing instead of having to do like red, green, or blue byte, right? Byte color. So cross-section, the cross-section color, right? Yeah. Okay, so let's try that. So let's put this over here, and then in my notes, I'm gonna say that this is byte 0 to 255. Okay, so that's a byte, and then we want to, at the very bottom, we want to return BYT. And is this returning a byte? Yeah, so that's the math for how I want to do that. And that is a little bit intense, I gotta say. I mean, it's not too intense, but it's like we got... If we look at our diagram, we got We got 16, we got 64, and we have 4, right? We have all these, like, magic numbers, 4, 16, 64. But this layout is not going to change, right? We've kind of, like, packed it in there and thought this is exactly how we're going to do it, right? Now, the next thing is we want... We also want to think of... Do we really want to use an abstraction where we think of it as a 512 by 512? And how is that going to... Yeah, we do want... So this will give us a byte value. But, there's no index value here, right? So we need a... We need a way to, we need a way to fetch by, index as well. And now we don't necessarily need to... We should probably only have one way where we're fetching. We should only have one fetching function, but we should have a way to fetch using the index. So, so I'm going to keep this as just a section here, and U32 VOB dex, and U32 instead of VI, it's we could use VD, like VD, or we could just do dex. Or VI looks easier. Here's what we're gonna do. So we're gonna make this, and VI. So let's go over into our little documentation section, and we'll do VI is voxel index 1D index Okay, so VI voxel index, and in here we're going to just try to convert a index into a So we're going to do VI 512. VI... So we're not going to call it VI, we're going to call it, VI 512. And the reason why we're going to call this VI 512 is because we want to make sure that we know that we're thinking of it as an index, but it's an index. The index is abstracted to think of the data as a 512 by 512 bitmap, even though our actual segment of texture memory we're using is 256 by 256. We're gonna think of it as 512 by 512 in here, so that if we want to, just because it's a useful abstraction to just think of our memory as 512 by 512. And the other thing is, we're only using a single byte of one of the channels, so the channels are like layered. There's a lot of overlap. There's not a unique one pixel represents multiple tiles, right? Depending on what channel we're looking at. So that's going to be a problem if we want like a unique integer handle that's going to locate the tile value. If we want a unique integer handle, then we need to get rid of that layering and just think of it as a 512 by 512 bitmap, right? So the reality is we really just have this 256 by 256 bitmap, and then we just use the different layers, right? But when we take those layers and when you take those different channels and we separate them and put them side by side, we conceptually have a 512 by 512, and we really want to stick with it like that. So let's stick with it like that, and we need to make sure that however we do the analogy here, it's compatible with whatever's going on here, right? So the first thing is we need to convert it to like an X and Y, but it's like a pixel X and pixel Y, but it's like a 512, right? So okay, so U32 pixel X 512 equals or actually pixel Y 512, right? Pixel Y 512 equals VI 512 divided by 512, right? And this is, we gotta convert that to float 32 first, and then we can trunc or int trunc. Okay, and so that's the number of filled strips we have. That gives us the Y value, and then U32 px 512 equals the py. We're going to take py 512, multiply it by 512, and then we're going to take the whole of it, and we're just going to subtract that out, right? So it's the remainder of what's left after we do that, right? Yeah, that's good enough. It's not going to line up quite right, but, yep, that's the math we want. Y, then X. Okay, so now that we have a X and a Y value, we need to figure out what our cross-section color is, right? Yeah, so we can get the cross-section color by, PX 512 Hold on. Yeah, so we should actually be able to do this. So we should be able to do PY 512 shift it over. Oh no, this is not. So it's not quite this. In our documentation, let's see. PX. P. So it's not quite this because, remember, this is still an... This is like a value that's 64 to 64. So what we're going to do is... we need to figure out what cell we're in. And the cross-section color, how do we get that? Cross-section color. Got ya. So, So C4X equals PX 512 divided by 64.0, and this is going to have to be a float 32. And int and trunk. And C4Y. Int trunk float 32 PY512 divided by 64.0. Okay, so cell for X, cell for Y. And the Y is, the Y determines the cells that have a higher value when we look at the linear value of them, when we order these cells. Instead of ordering it, so this could be 0 or 1, this could be 0 or 1. But Y determines the higher valued cells. So this is the more significant bit, so it's going to be shifted over 1, whereas this is going to be shifted over 0, right? So that makes sense. So now we have the cross-section color, and it's just the same as this exact variable, right? We're using the exact same variable name, right? So we can do C4X, and that is going to be that is the we can make a little note here. So these diagrams are getting way out of hand, but, you know, it's... So, C4X, 0... C4Y equals 1. And, right, we have the shifting here, 0, 1, 2. And, right, we can keep some sanity there, and I didn't realize that we would have to... Oh, I see why we did it that way. My bad. Okay. So the X value, the cell 4X value, right? Because we have this 4x4 cell kind of thing here. The X is, for this cell right here, is 0. The Y is 1, and the cross-section color is 2, right? And in binary, that is We take the y, we shift that over, 1 and 0, right? And 1 and 0 is 2? Yeah, because 0 is 0, 1 is 1, and then 1 shifted over would be 2. Okay, that makes sense, yep. And then if we added another one, yeah, so that makes sense to me, where this kind of math makes sense. So x and y, cross-section pxy. Okay, so once we have the cross-section color, once we have the cross-section color, are we pretty much done, or what else needs to be done here? So So to get the pixel x, pixel y, like the actual pixel x, pixel y, is that going to be correct? So we want to make absolutely sure that we are fetching the data exactly the same as we Okay, so this isn't quite right. This isn't quite right. The first thing so this is a three-dimensional value right here. This is or is it? Yeah, this identifies a voxel. This identifies a voxel in our 64 by 64 by 64 volume by mapping to a 512 by 512. And therefore, I think our math is not quite right, because we were only thinking of x, y, and z. Well, let's think about it for a second. Yeah, this is confusing, having these two different translations between what's what here. What's the utility here? What's the utility? Why do we want this 512? Okay, we want the 512 because we want just one number that identifies the x, y, and z. The next thing is that not only is it a number that identifies the x, y, and z, but it corresponds directly to an x and y on a two-dimensional texture, right? So we can take this index, and from that index we can just identify a pixel in a two-dimensional array. So no, this would be correct then, right? Because we take this index, and this index may have once upon a time encoded some three-dimensional information, but now it's just a 2D index, and we just use it in our 512 by 512. However, when we're using a 512 by 512, how are we going to store the Okay, and when we're using it in a 512 by 512, we're just going to store the when we store it in a 512 by 512, we want to keep a similar layout to the 256 by 256, right? And the idea is that eventually when we're actually using a 512 by 512 texture, that we're just going to get a bonus of 4 more layers or more than 255 possible tile values, right? We'll get like this. We'll get this bonus, right? So we'll get like it'll be like a little expansion pack, right? But we want to figure out an engine that can work with just that 1 byte, 0 to 255 for the tile values, and then when we're actually working with the whole 512 by 512 section of memory, we can take advantage of those extra slots for some other features, right? So we have that free space that we can kind of work with to do something extra with later. And that gives us room to expand, and it also kind of constrains what we're currently doing so that we don't get out of hand here. So it does make sense that I was abstracting this only in 2 dimensions. So another thing is we're gonna give some more things names here. We're gonna call it DO1. And okay, so we're gonna we're gonna say map onto DO1. Okay, map onto conceptual 512 by 512 bitmap DO1. And then here we're just trying to figure out which of those cells we're in. Find cell Okay, find cell color quadrant. And okay, so find cell color quadrant. And the question is now, how do we make sure that we're mapping this to the... We want the end result pixel to be exactly the same as what's happening over here, right? So how are we gonna do that? Well, this controls the Z, right? So we need to like get back to Vx, Vy, and Vz so we can go back into here, right? We're gonna... So... Huh. I'm not sure I want to do that. So... how does this map back to the... I guess we just need to get the correct X, Y, and Z, right? We just need to get the correct X, Y, and Z. And in the end, we're going to return vob XYZ with Vx, Vy, and Vz, right? So this is an abstraction on top of vob XYZ, because this dex has to be, even though we're overlaying our bytes, we have to, right? So this actually goes down here because it uses the other one, right? So let's put that there like that, and so vob dex uses vob XYZ. And to get this VZ, VZ is pretty easy. So U32 VZ equals the cross-section color. We just take the cross-section color and we multiply by 16. And we can even look at this and we notice that we're dividing by 16. So if we want to undo that, cross-section color multiplied by 16, it gets VZ, right? Cross-section color times 16.16, or U32 16, right? Okay. And these all need to be U32s. I don't see them declared anymore, so let's U32. And once we have VZ, we need to know, like, what's the X and Y, right? And the X and Y are, we're still doing, like, the collisions here. So we're still kind of colliding into, oh, hold on. Cross-section color. That's truncating it. Okay, yeah. So this isn't quite right. It's we take the this would be the base. This is some type of local base value, but it's not this is some type of yeah, this is some type of this is some type of base value, but it's not it's not exactly the Z value, right? It's not the cross-section local. It is Okay, so CSG. So we're looking at this cross-section color, right? And VZ. We're gonna take VZ divided by 16 to figure out the first cross-section color, right? The cross-section color, which section of floors we're on, right? And then, if we want to know globally within the skyscraper, like not taking into account what color the floors are, what the global z value of that is, then that would be the global first value, right? The global first value. Let's not call it. Let's call it CSF because it's the first. It's the first floor of the whatever colored floor we're on, right? It's the first floor of whatever colored floor we're on. And if we want to get the local floor color, then we take the global first floor color, and we take VZ and we minus the global first floor color, and now the local floor is the local index within the set of floors that are all the same color, right? Section first floor of given color. CSG. Not used. FG for global. Okay, so CSG kind of means like global floor index, but we're going to go with CSF for the first floor of a certain color. Maybe that's not the way we want to think of it, but let's just go with CSF. And then to get the local, we'll take that first floor globally, and we'll subtract that. Yeah, sure. Sure. What we'll use F. So CSF is that first floor. So going back here, we had some confusion here, and we thought this was like VZ, but now when we kind of like break this logic apart a little bit more, we see CSC times 16 equals CSF, right? And then down here, CSC times 16, right? So that is not VZ, right? It's that global offset of CSF, right? So now we can go And now that we've broken up the equation a little bit more, we don't know what VZ is, but we know that CSF equals that, and then U32 CS VZ. I don't know what that is yet, but let's look at how we can calculate that. So we need the local floor. How do we get the local floor? Well, to get the local floor, to get CSL, right? CSL can be derived backwards from here using this X and the Y, and the X and the Y is okay, this is the okay, these are the offset origins, right? Because we take the CSX and CXY. Okay, so looking at that, we need to get so we're gonna see what we have to see which grid cell we're colliding with. I'm a little bit I'm tired though. Okay, so I'm tired, so we're going to finish this later, and we're gonna make sure that we have this mapping correct, because I'm not sure if we have this mapping correct, but we'll be like, blah blah blah, to do finish this. Right. So we'll get to that at another time, because I'm kind of tired here. Let's see, what do we have here? Do we have a shader toy for SDF19? That's what we're working on here. It is, it's unlisted. So let's look at, can we just hit save here, make sure that's still good? Okay, let's look at what we have on... Do not know how these notifications work. Yeah, well, let's keep on looking at this for a second. When we're thinking about the X and the Y, voxel X and voxel Y are within one of these 64 by 64 cross sections. So I believe what it is, let's look at our variables really quick. We're gonna change that to CQX. Okay, so we'll make a note here. Now that we've changed that, so with the CQ, we'll make a note here. So not. Okay. So, U32 CSX. Um, well, first we need a. So I think we can calculate the pixel X, we can calculate this actual pixel X value, I think, by taking, no, we need the local. No, we need the local, so... Mm-hmm. This is not correct. Should be 256. And 256. Oh wait, no, 64 by 64. Okay, so I need a clearer idea of how these are all related to each other. I'm not quite sure what that is right now. So I'm gonna give up for now. I'm done for now. I'll try to figure that out later. It's just important that, well, the only thing I'm doing differently Yeah, this should be, I think this should be 256. What color floors are you on? Alright, so we're going to take the conceptual 512 by 512, and if we divide by 256, we figure out which one of those quadrants we're in, right? And then to get the to take this pxpy to the non-conceptual, we'll take the px512, we'll take that quadrant, and we'll times that by 256. And to get the non-conceptual map conceptual 512 by 512 xy to Okay, so we're going to map the conceptual 512 by 512 to the actual 256 by 256. And all we got to do by that is we figure out which colored quadrant we're in, the red, the green, the blue, or the A, or the alpha. And that is either a... Uh, 512 divided by 256 is 2. So CQX, where do I get C? Well, the thing is that we're never going to get 512, right? Because it's 0 to 511, right? And if we do 511 divided by 256, we get 1.9999, right? And that's going to truncate to 1, right? And if we're at 256 divided by 256, well, we obviously have 1 because that's the first. That is the first pixel of the second cell, right? Okay, so this makes sense. The value should be either 0 or 1 here. And then we multiply by either 0 or 1, right? And then that gives us the 256 times either, yeah, so that'll give us the actual x or y, right? And then for the cell cross-section, right, now that we have the actual xy value, we can take that xy value and we can map it into our grid subdivision, where we take a whole bunch of 64 by 64 cross sections in a grid that's 4 by 4. It's 4 by 4 cells, but it's 64 by 64 cross sections. So does that mean we divide by 4 or we divide by 64, right? Well, the width is 64 and the output should be 0 to 3, right? So CSX, yeah, CSX, CSY, yeah, the output should be 0 to 4. So, so we should divide by 64 there, right? So we divide by 64 to get the CSX, CSY cell value. Get 2D representation of floor of red GB of your colored floor. Okay, we're gonna get a 2D representation of our colored floors. And with that 2D representation, we can convert it to, do we need to convert it to index? Is that index necessary? 0, 1, 2, 3. Yeah, because that index gives us the z value, right? We don't know the z value yet, right? And that index will give us the index will give us the z value, right? Yeah. As far as the x and y, we can just derive that from the final x. So Vx equals we take the pixel x 256 and we minus the cross section x, which should be 0 to 4, times we multiply that by 64, right? And then Vy is Px 256, so our actual range of values. And we got to do some grid collision to figure out where we are, and we'll do CSY times 64. Right, so we're going to take those excess, and we're going to, well, hold on. No, we're not taking px and minusing it at all. We're just taking, oh, wait, because this is a local. Vx, Vy is local cross section inside CSX CSY cell. Right? Okay, so Vx, Vy is a local chord inside the CSX, CSY cell, and that's why we actually take this and we take the Px, Py actual, and we subtract this because we want to localize this, right? We want to get the local cross-section coordinate, right? So then the Vz is the index value of CSX, CSY, right? Okay, so Vz is the index value, so we'll do like index to xy. Okay. And that's not the index to xy calculation we need, so we need so Vz equals CSY times 4, because the width is 4. plus the remainder, whatever's left over, right? So CSY locates the full lines, and then CSX would be the remainder, so CSX. Okay, yeah, so that makes sense. So those are all the values, I think. So CSX, CSY. What about this floor here? We have this floor, and why are we not using it? That is kind of concerning. So this, okay, so I see what this is about. So, true, but not needed here. Okay, so there's a lot of, like, calculation where, when we use this index, we kind of, like, we do some calculations, and then we kind of, like, undo those same we do some calculations to, like, get Vx, Vy, Vz, only to, like, undo some of those calculations here. But the idea is that we want to keep this consistent abstraction with this mapping, right? So this index is a index locating the XYZ of our voxel, and it's as if the index were mapped onto, as if that index existed on a 512 by 512 bitmap. So let's look at what definitions we have here. So VI 512 by 512, we have that, and so PX 256, PX actual location on real 256 by 256 bitmap. Okay, so PY256 is PY actual location on 256 by 256 bitmap, right? And CSX, CSY, where is that? Okay, yeah, so I think we had, we might want to make a note. I think the most important part is that, I I think the most important part is that we coded this while looking at tile data layout, and because I think that really helped us. That really helped us make sure that that was correct, right? Yeah, I think that's right. And then let's look at what else we got. We got vob xyv, vob dex. So I'd say we have all of our variables are accounted for here. Some of this math will probably need some checking, but I'm kind of tired, and I think I got the basics of it, where I have where I've kind of figured it out. So we're gonna keep on going tomorrow and making more weird-ass diagrams to try to figure stuff out. But I'm tired, so I'm done here. So later.